Hello, everyone. Welcome to this online course on building materials. I'm your lecturer for today, Wan Ying. In this lesson, we will study the technical requirements for aggregates used in normal concrete. In construction engineering, aggregates are granular materials that serve as a skeleton and filler in concrete and mortar. They are also known as aggregates. Based on particle size, aggregates are classified into fine aggregates and coarse aggregates. Since aggregates account for a large proportion of concrete, their properties significantly influence the performance of the concrete. Knowledge objective of this lesson: to become familiar with the technical requirements for both coarse and fine aggregates. Competency objective: to develop the preliminary ability to correctly select coarse and fine aggregates. Professional quality objective: to establish the engineering concept that materials define the foundation and details determine success or failure, while cultivating a rigorous and responsible professional attitude. First, let's study the technical requirements for fine aggregates. Fine aggregates are classified into categories 1, 2, and 3 according to technical requirements. According to Sand for Construction, GB/T14684-2022, the main technical requirements for fine aggregates include fineness and particle grading, clay content, stone dust content, clay lumps and deleterious substance content, soundness and crashing index, and the content of flaky particles. The fineness of sand refers to the average degree of coarseness of mixed sand grains with different diameters, expressed by the fineness modulus, mx. Based on its value, sand is categorized into coarse, medium, fine, and extra fine sand. Under the same dosage, excessively fine sand consumes more cement and leads to greater long-term volumetric shrinkage, while excessively coarse sand easily causes segregation and bleeding. Therefore, to ensure concrete quality and save cement, medium sand is preferred. Particle grading refers to the distribution and arrangement of sand grains of different sizes, expressed by grading zones. To save cement and improve concrete strength, the voids between sand grains should be minimized. As shown in the diagram, a combination of multiple particle sizes results in the lowest porosity. Therefore, to reduce the voids between sand grains, there must be a rational combination of particles of various sizes. Good particle grading of sand not only saves cement consumption but also contributes to the improvement of workability, strength, and density of the concrete. The fineness and particle grading of sand are commonly evaluated using the sieve analysis method. The sieve analysis method involves using a set of standard square hole sieves with apertures, net sizes, of 4.75 mm, 2.36 mm, 1.18 mm, 0.6 mm, 0.3 mm, and 0.15 mm. A 500 grams dry sand sample is sieved through these sieves in order from coarse to fine, and the mass retained on each sieve is then weighed. Then, the individual percentage retained and the cumulative percentage retained for each sieve are calculated. Based on the cumulative percentage retained, the fineness modulus of the sand is calculated and the grading zone is determined to evaluate the fineness and particle grading of the sand. The formula for calculating the fineness modulus of sand is as follows. A higher fineness modulus indicates coarser sand. For sand used in concrete, the fineness modulus ranges are 3.7 to 3.1 for coarse sand, 3.0 to 2.3 for medium sand, 2.2 to 1.6 for fine sand, and 1.5 to 0.7 for extra fine sand. The particle grading of sand is divided into zones 1, 2, and 3 based on the cumulative percentage retained on the 0.60 mm sieve. The compliance of the sand grading is determined by the grading zones or the sieving curve. Zone 1 sand tends to be coarse. When using it, the sand ratio should be appropriately increased to satisfy the workability requirements of the concrete. Zone 3 sand tends to be fine. When using it, the sand ratio should be appropriately reduced to ensure concrete strength. Zone 2 sand is moderate and should be prioritized when proportioning concrete. Sand often contains impurities such as clay, silt, organic matter, mica, sulfides, and sulfates. Clay and silt adhere to the surface of sand grains, which hinders the bond between the cement and the sand, reduces the strength and durability of the concrete, and increases drying shrinkage. A suitable amount of stone dust in manufactured sand is beneficial to concrete, but an excessive stone dust content will adversely affect concrete performance. Mica has poor bonding properties with cement, which reduces the strength and durability of the concrete. Organic matter, sulfides, and sulfates all have corrosive effects on cement. Chlorides accelerate the corrosion of steel reinforcement within reinforced concrete. Therefore, the clay content, stone dust content, clay lumps, and deleterious substance content in the sand must comply with the following regulations. The soundness of sand refers to its ability to resist disintegration under the influence of external physical and chemical factors. For natural sand, it is typically expressed by the mass loss after 5 cycles of wetting and drying in a sodium sulfate solution. For manufactured sand, the crushing index is used for representation. Flaky particles in sand refer to particles in manufactured sand, with a diameter above 1.18 mm, whose minimum dimension is less than 0.45 times the average diameter of their respective particle size class. Excessive flaky particles will reduce the fluidity and strength of the concrete mixture. The content of flaky particles in category A manufactured sand should not exceed 10%. The apparent density of sand should not be less than 2,500 kg per cubic meter. The bulk density should not be less than 1,400 kg per cubic meter, and the void ratio should not exceed 44%. The radioactivity of sand shall comply with the regulations of GB 6566. Alkali aggregate reaction, AAR, refers to the expansive reaction between active minerals in sand and alkalis from the concrete components or the environment, which occurs slowly in damp conditions and leads to cracking and failure of the concrete. When requested by the purchaser, the measured expansion rate and alkali activity evaluation results must be provided. When the purchaser specifies requirements for moisture content and saturated surface dry (SSD) water absorption, the actual measured values must be presented. Next, we will study the technical requirements for coarse aggregates. Coarse aggregates are classified into categories 1, 2, and 3 based on their technical requirements. The standard pebbles and crushed stone for construction, GB/T14685-2022, specifies the main technical requirements for coarse aggregates as particle grading and maximum size, clay content in pebbles, clay/dust content in crushed stone, clay lumps and deleterious substances, content of needle-like, elongated, and flaky particles as well as irregular particles, strength and crushing index, and soundness. The principle of grading for coarse aggregate is basically the same as for fine aggregate. It also requires good particle grading to reduce porosity, save cement, and improve the density and strength of the concrete. The particle grading of coarse aggregate is also evaluated using the sieve analysis method. Particle grading of coarse aggregate includes continuous grading and single-sized, gap, grading. Stones with continuous grading have a rational size distribution, which results in good workability of the concrete mixture, prevents stratification and segregation, and requires less cement. Therefore, continuous grading is preferred for stones used in concrete. Single-sized grading is generally used to combine into a compliant continuous grading, or it can be mixed with continuous grading to improve its distribution or to produce a continuous grading with larger particle sizes. The particle grading of pebbles and crushed stone must comply with the specifications in the table. The maximum particle size of coarse aggregate refers to the upper limit of the nominal size range of the stone. The specifications of stones are expressed by nominal size ranges. For example, for stones with a size range of 5 to 20 millimeters, the maximum particle size is 20 millimeters. As the stone size increases, the total surface area decreases, which saves cement. Under specific workability and cement dosage conditions, it can also reduce water consumption and improve concrete strength. Therefore, within permissible limits, the largest possible maximum particle size should be chosen, though it is restricted by factors such as the cross-sectional dimensions of the concrete structure and the clear spacing between steel bars. The Standard for Quality Control of Concrete, GB 50164-2011, stipulates the following. 1. For concrete structures, the maximum particle size of coarse aggregate shall not exceed 1/4 of the minimum dimension of the component's cross-section and shall not exceed 3/4 of the minimum clear spacing between steel bars. 2. For solid concrete slabs, the maximum size of the aggregate should not exceed 1/3 of the slab thickness and must not exceed 40 millimeters. 3. For mass concrete, the maximum particle size of coarse aggregate should not be less than 31.5 millimeters. 4. For high-strength concrete, the maximum particle size of coarse aggregate should not exceed 25 millimeters. Like fine aggregates, coarse aggregates must also have strictly controlled clay content in pebbles, clay/dust content in crushed stone, clay lumps, and organic matter, sulfide, and sulfate content. Otherwise, the strength and durability of the concrete will be compromised. In addition, the content of needle-like/flaky particles and irregular particles in coarse aggregates must be limited. An excess of needle-like and flaky particles will reduce the fluidity of the concrete mixture and affect its strength. Irregular particles can affect the fluidity, strength, and durability of the concrete. Therefore, coarse aggregate particles for concrete are ideally cubic or spherical in shape. The strength of crushed stone can be expressed by the cubic compressive strength of its parent rock and the crushing index value of the stone. The strength of pebbles is expressed by the crushing index value. The compressive strength of the rock should be at least 20% higher than the design strength of the concrete. When the concrete strength grade is C60 or higher, the compressive strength of the aggregate rock must be tested. For routine production quality control and engineering, the crushing index test is utilized. The compressive strength of the parent rock used for crushed stone must comply with the specifications in the table below. The crushing index represents the stone's resistance to being crushed. A lower crushing index value indicates a stronger resistance to fragmentation. The crushing index must comply with the specifications in the table below. The soundness of crushed stone and pebbles should be tested using the sodium sulfate solution method and expressed as the mass loss of the sample after 5 cycles. The requirements for alkali aggregate reaction and radioactivity for coarse aggregates are the same as those for fine aggregates. The apparent density of crushed stone and pebbles shall not be less than 2,600 kilograms per cubic meter. And the loose bulk density void ratio and water absorption for continuous grading must meet the requirements in the table. Upon request by the purchaser, the actual measured values for moisture content and bulk density must be provided. In this lesson, we have studied the main technical requirements for coarse and fine aggregates in normal concrete and clarified the significance of applying relevant national standards in actual engineering projects. Aggregates may seem ordinary, but they are the skeleton of concrete. Their quality directly affects the safety, durability, and economic efficiency of engineering projects. I hope you will always uphold a rigorous, pragmatic, and excellence-oriented professional attitude. Deeply understand the scientific principles and safety considerations behind material standards. Solidify your professional foundation and build safe, high-quality, and green construction projects. That's all for today's lesson. Thanks for your attention. See you next time.